Global food security is a major challenge to humankind. We have to improve, almost double food production by 2050 to meet the demands of the projected increase in human populations. And to do this, we obviously want to make agriculture more productive, but at the same time we want to make it more sustainable. So we want to use lower chemical inputs if possible. In addition, many third-world farmers have no access to these chemicals. The aim of the research is to basically make plants more nutrient use efficient so they can do more with less. Up to this point in time, researchers are focused on the top part of a plant to improve yields. What we're proposing is to actually look at the hidden half of plant biology, which is essentially the roots. And the roots really play a key role in terms of nutrient uptake, and they can make all the difference. The big problem to date has been our inability to see roots in soil. The real breakthrough has come in new imaging technologies which are based on X-ray, micro-CT systems. These are systems people use in hospitals. Applying them now to actually look at root systems, so to understand the 3D architecture of how they populate the soil and take up nutrients. So by using this new technology, which is being developed in collaboration with two researchers at University of Nottingham, Sasha Mooney and Tony Pridmore, we're developing the technologies to actually take the images and also reconstruct them to really understand how roots interact with the soil environment. What we want to do then is to look at the current crops to see how their roots grow in soil and how they can be improved. So for example, if you want to take up a nutrient such as phosphate, this tends to accumulate in the topsoil. And so what we really want to do is to re-engineer crops so their roots populate the topsoil more efficiently. If we want to make crops which are more drought resistant, we obviously want to increase rooting depth. So it's a question of using this imaging technology to select for the varieties which actually have these adaptations, the desirable changes to root architecture, and then bringing that into breeding programs. The University has been tremendously supportive. They've provided funding for the imaging equipment I described. They've also provided funding for PhD students, and there's been a huge push as part of the University Research Excellence Framework to actually support these root studies, so of which I'm very grateful. Well, my wife would say I'd commit too much time to this, but I've worked for 20 years on roots, and so I've literally worked in the laboratory. We tend to grow roots, study roots grown on agar plates, and that's not very realistic. And so I recently got a fellowship from the UK funding agency, the BBSRC, of which, and the real challenge was to actually take my research into the field and to study roots in a more natural context. So this is where this imaging approach was really critical, to actually now see the roots and how they grow and develop in the soil.